based on what we talked about atomic radius yesterday, go ahead and answer this one in your notes. New code. Okay, who has an answer to this particular question? I want an answer and why. Which of the three has the largest atomic radius? Who wants to take a stab at it? Raise your hand. There's a space. Go ahead, Grace.
Magnesium.
Yep, why?
Not gonna lie, I just saw that it was closest to the end, so I chose
Yeah.
it.
So the answer is because according to the trend, the further left you are, the bigger you are. The further right you are, the smaller you are. Do we remember why? Talked about that yesterday too. Go ahead.
Because isn't it the attraction between?
Yeah. So as we move left to right, okay, we gain a single electron and a single proton as we move from one to the next, right? That single electron gets added to the same energy level, and that proton gets added to the nucleus. Because the electron's being added to the same energy level, all we're doing is increasing the force of attraction between the negative and the positive, okay? So as we increase that force of attraction, we decrease the radius, okay? All right. Our next trend is going to be described by a concept called ionization energy. An ion is defined as something that loses or gains an electron, which means they have a positive or a negative charge when they do so. The process of creating an ion by either removing an electron or gaining an electron is referred to as ionization. And there's always energy involved in the creation of an ion. So whether we're trying to remove an electron or we're trying to put an electron onto an atom, there is an amount of energy required to do that. The amount of energy required to remove one electron, the first electron from a neutral atom, is going to be referred to as the ionization energy. Specifically the first ionization energy, because we're only taking one electron off. The first electron we take off is going to be the first ionization energy required. So there's the concept behind an ionization energy. The trend is the next thing. There are, of course, two trends, just like there were in our first one, atomic radius. The first trend talks about when you go left to right. Ionization energy is the main group elements. Remember, what does main group mean? Anybody recall from yesterday what we mean when we say main group elements? Go ahead, Cole.
Is it the people at the mass one?
It's the S and the P block only, so we ignore the transition modes in the F block model. As we move left to right, it becomes increasingly more difficult to remove an electron from the outer energy level of an atom. Because remember, they're being sucked in. There's that increased force of attraction between the electrons and the protons. It becomes harder and harder to overcome. It requires more and more energy to do so. So, ionization energy goes up, increases as we move left to right. In the main group elements, in most groups in general, as we go down, electrons get further and further apart. Electrons get further from the nucleus, which means the amount of energy required is less. The further away the electrons are, the easier they are to remove, less energy required. Alright, so just to kind of show you what we're seeing here, and to reiterate the idea that a trend is a general thing, over here we see, on the left, as we move from left to right, the ionization energy goes up. As we move from left, so lithium over to neon in period 2, the ionization energy generally increases. Do you see these little parts where it doesn't necessarily always increase? That's what we mean when we say this is a general trend. We can talk about what we think will happen, but at the end of the day, there's probably something a little more complicated going on than our trend can explain. Okay? Alright. So let's consider two main group, meaning S and P elements, A and B. One has an ionization energy of 419 kilojoules per mole, and one has an ionization energy of 1,000 kilojoules per mole. Which of those two, A and B, do you think should be in the S block? I'm calling somebody else today. Mallory, what do you think? There's only two options, A or B.
A.
Why? So what did we just say about ionization energy? What happens as we move left to right?
It increases.
Okay, so the things on the left should be lower than the things on the right, correct?
Yeah.
Is S on the left or the right?
The left.
On the left, so it should have the lower ionization energy. So
Yeah.
A is in the S block. By definition then, B is where? The P block, because it has a higher ionization energy. Which of those two then is more likely to give off an electron and become positive? Go ahead, Cole.
S, or the element A.
Yep, element A, which is in the S block. Less energy required to create the ion means that it's the one that's more likely to form the positive ion. Alright. Our next concept is electron affinity. This is going to be the opposite of ionization energy. This is the energy required to create a negative ion, in other words, to add an electron to a neutral atom. As we move left to right, things on the periodic table tend to like to gain electrons, so electron affinities go up. As we move down a group, the opposite occurs. Electron affinity goes down because when we gain an electron, it's further and further away from the nucleus. to talk about are the last major concepts in this chapter involving ions. First thing is to talk about ionic radii. When an atom loses an electron, it becomes more positive and forms what we call a cation. Since a cation is losing an electron, cations tend to be smaller than their neutral counterparts. Again, we call these things cations because they've lost an electron. On the opposite side of the spectrum, we have the formation of anions, which have gained electrons and gotten larger. When we think about the difference between a neutral atom and its cation counterpart, any neutral atom that loses an electron becomes a cation, has lost an electron in the first place, which means it's getting smaller. So if we look at all of one row, say row 2 on the periodic table, if the entire row loses a single electron, all of them have a positive 1 charge, and they all get smaller than they were before. Which means that as you move left to right, for cations specifically, things are going to decrease in size just like they did when they were neutral. And as you go down, things are going to get larger, but only marginally. Same thing applies to anions. If everything gains an electron, everything gets bigger. That being said, even if everything has only gained a single electron, everything still gets smaller as you move left to right, and gets bigger as you move top to bottom. Ionic radii will follow atomic radii. If and only if everything in that row has the same charge. As we go down, we're just increasing the amount of stuff we have, and we're adding it to a more and more outer radius of our specific nucleus. As we move down, we gain more and more electrons, which means we gain more and more energy levels. The further away the energy level is, the more electrons it can hold, and the bigger the atom gets. Increase ionic radii as you go down. Alright, next major topic is on valence electrons, one of which you've actually already read about. in chapter 4, section 3, valence electrons were introduced. For us, we're going to refer to these as the electrons that can be lost or gained or shared between two atoms. These are the electrons that are in the highest energy level of an atom, furthest from the nucleus. Okay. And these are all going to be typically referred to in the main energy way. In other words, 3s, 3p, or s and p blocks specifically as far as electrons are concerned. These are the electrons involved in chemical bonds and creating molecules. The only location you can add or remove electrons from is the valence electrons. Again, furthest from the nucleus, highest energy level as far as distance. Involved in bonding. That brings us to our final concept in this chapter, known as electronegativity. If valence electrons are the things that are going to hold chemical compounds together, then what we need to decide is which side of a chemical bond holds on to the electrons a little tighter than the other. And to do that, we're going to use a concept called electronegativity. Electronegativity is going to be defined as how good an atom is at hogging electrons. We typically move away from talking about individual electrons when we talk about electronegativity, and we talk about a concept called electron density instead. To understand electron density, I want to remind you that there is only one atom on the periodic table that has a single electron, and that's hydrogen. Everything else has more than one, and more than one electron means that a lot of electrons can be doing the same thing at the same time. So a cloud of electrons can unevenly distribute itself between two atoms. And when we talk about electronegativity, we want to talk about how good is one atom compared to another at attracting electrons toward it. We call it hogging the electron density. As we move left to right, electronegativities increase, and as we move down a group, they decrease. To visualize this, the most electronegative atom on the periodic table is fluorine, F. As you get closer and closer to fluorine, things get more electronegative. As you get further and further away from fluorine, things get less electronegative. So think of fluorine as the X on the map, and the closer you get to it, the more electronegative you become. What is the exception to electronegativity because they are unreactive?
Noble gas.
The noble gases. They do not count in this particular type of trend. Good. That brings us to our POBO. POBO we're going to do today, we're going to start today, we won't finish, is going to cover periodic trends. Okay, so you're going to go through and you're going to read some information and you're going to look at evidence of the different trends that we've discussed in class so far. What I'd like you to do